Tautomerism. Tautomers are structural isomers. These are structural isomers. Usually, they are formed by the relocation of hydrogen atom. The structural isomers are known as tautomers, and phenomenon is known as tautomerism. And these tautomers, that is these isomers are readily interconvertible. Then look at some examples. The common examples coming under tautomerism are, first one, keto-enol tautomerism, nitro Rc tautomerism, then Amido and Amidol tautomerism. The first one is keto-enol tautomerism. Keto-enol tautomerism will happen only when the carbonyl group having an alpha hydrogen. That is, if the compound containing an alpha hydrogen to carbonyl group, then only the keto-enol tautomerism will obtain. So let us look at an example. Okay. CH3CO CH3. CH3CO CH3. This is a keto form. This is acetone. Okay. If you look at this compound, that is, if you look at acetone, we can see two alpha positions are there. This is one of the alpha position and this is the second one. Two alpha positions are there, but we require only one alpha position to show how this keto-enol tautomerism works. Then we represent tautomers by placing double arrows in between them. Okay. For our convenience, I am going to rewrite this alpha carbon like this. Okay. During keto-enol tautomerism, one of the hydrogen will be relocated from the alpha position, and we can represent the bond shift like this. This hydrogen bond, carbon-hydrogen bond will be shifted towards this carbon-carbon single bond. At the same time, the oxygen, carbon-oxygen double bond will be shifted towards oxygen. So, the tautomer formed from this keto form will be like this. Carbon, two hydrogens will be there. Then the single bond will be converted to double bond. And here double bond is not there, only single bond attached to an O- group and a CH3 group. This is the enol form. And why this is enol? An OH group is there. That means the shifted hydrogen from the alpha position will be attached to this O- and this will be converted into OH. That is why this is enol. That is double bond attached to an OH group. The second example is Nitro Rc form. In almost all tautomeric forms, we need alpha hydrogen. Here, the group present, the functional group present is a nitro group, that is NO2, N double bond to O, O- group. And this nitrogen group, this functional group is attached to a carbon that should contain a hydrogen atom. Then only this tautomerism will occur in this compound. So, nitro Rc tautomerism will obtain when nitro group attached to an aliphatic group containing an alpha hydrogen. So, now the mechanism is clear. The formation of tautomerism is clear. The hydrogen shifted towards here and the double bond shifted here. So carbon, hydrogen, hydrogen, double bond N, here O minus, and readily O minus will attack hydrogen and it will be converted to OH. Here O minus. The C double bond N attached to OH group is known as ASI compound. Okay, due to the formation of ASI compounds, nitromethane, due to the formation of this ASI form, nitromethane and nitroethane acts like acid, and they are considered as pseudo acids. And the acid nature of this compound is due to this group. If you look at this group, it is almost similar to the carboxylic acid group COOH-O minus. And these compounds are considered as pseudo acids because due to the formation of this acid tautomer. Then next one, Amido Amidol tautomerism. Amido group means carbonyl group attached to NH2 groups. Both sides NH2 group, and here alpha hydrogen is present. Here also alpha hydrogen is present. If you represent the tautomer, this will like, okay, I'm going to write this alpha hydrogen like this. So if you draw the tautomer, this hydrogen bond is shifted towards here, shifted between nitrogen and carbon, and at the same time carbon oxygen double bond shifted towards oxygen, and the tautomer will be like this: NHH double bond C and OHNH2. This is amidol. Okay, these are some examples coming under tautomerism. Okay, if we talk about the characteristics of tautomers, these tautomers exist in dynamic equilibrium. Dynamic equilibrium exists between them. That is CH3COCH3 exists. The tautomer, enol tautomer of this is CH2 double bond COH-CH3. This keto form and enol form exist in dynamic equilibrium. And in suitable conditions, we can isolate this tautomers. By applying some suitable or in some suitable condition, we can isolate keto form. Sometimes we can isolate enol form also. And this isomers, these tautomers differ by their stability. They differ by stability. In some cases, one of the tautomer will be more stable, and in some case, the other one will be stable. That depends upon the compound we are considering. Okay. If we look at their structures, this is much more resembles to a resonance phenomenon. But actually, this tautomerism is not that much resembles to resonance. So coming to the next section, that is what are the difference between resonance and tautomerism. So resonance versus tautomerism. If we draw the resonance structures of benzene, simply we can draw the resonance structures of benzene. So the structures will be like this. And if you are representing the keto-enol tautomerism, this is C, we want to CH3, and the tautomer will be CH2 double bond COH and the CH3. By simply looking these structures, we can easily say that resonance is represented by placing a double-headed arrow in between these structures, in between resonance structures. And in tautomerism, we use double arrows. Actually, that is not the difference between tautomers and the resonance structures. So, the tautomers are really exist. That is, their existence is real. But resonance structures are just hypothetical structures. We use resonance structures to identify the correct structures. We know none of the resonance structures are real. The real structure exists between these resonance structures. We don't know what is the real structure of benzene, but we represent this resonance structures which is very comparable to the real structure. So resonance structures are hypothetical structures. They help us to find the real structure. Okay, so these are hypothetical structures, but tautomers are real structures. So as these structures are hypothetical structures, there is no equilibrium between these structures. There is no equilibrium between these structures. Actually, there is only one structure, but all these structures resembles to the real structures. That is why we represent all these structures. Okay, but tautomers are really exist, so there is a dynamic equilibrium in between them. Here, if we look at these structures, we can say that this resonance are represented by the delocalization of pi bonds. Here this pi bond is shifted towards here, so on. But here relocalization of hydrogen. Okay. Resonance increases the stability. But no such stability change occurs here in tautomerism. But I already told that one of the structure will be more stable than the other. But due to the tautomerism, the stability will not increases. So no such process. Stability will not be changed by the process tautomerism. Okay, but we should remember that one of the structure will be more stable than the other, and which one is the more stable structure, that depends upon the compound. Okay, these are all the differences between resonance and tautomerism.